Welcome to Part 2 of the Standalone Training's video component. We hope you enjoyed learning about the different parts of the KEE system while watching the first part of the video and working through the tutorials. This part of the video will look in more detail at how you can use the KEE tool chest to build an application. It will be most helpful after you have gone through the tutorials and are ready to work on your application. But if you haven't had time to work through the tutorials yet, you may want to watch this video now and watch it a second time later. We'll first look at some initial considerations like defining and narrowing down a problem. You'll also hear about some concerns novice users usually have. We'll look at some questions concerning the representation of your domain. Then we look at forward chaining versus backward chaining when reasoning using rules and look briefly at efficiency issues. Following that, we discuss object-oriented programming in KEE. You'll see how this programming style has been used in the Gates demo to make it more transparent and easier to expand. Next, we'll look at the development of the end-user interface for the Gates demo, and you'll learn about some factors determining interface design. Finally, we'll talk about portability, to make it easy for you to have your application run on a variety of platforms. The Gates knowledge base was not actually built by an airline. It was designed especially for this training, since we wanted to be able to send you the knowledge base with your training materials. However, the development cycle of the project we present here is similar to projects we see among IntelliCorp customers. And while there is an emphasis on the parts of KEE you learn about in this training, the use of features in general is also similar to that in applications we've seen. For this video, my colleague here will ask questions we often hear from people that just learned about KEE and that may be on your mind as well. I'll take the part of the demo builder, answering questions and pointing out some interesting aspects of the project as we go along. There will also be short presentations by knowledge engineers and senior technical staff from the IntelliCorp team about the topics we discuss. When we started developing the Gates system, there were a number of questions we had to ask. So we went to David Michelovich, Director of Applications at IntelliCorp.
Success requires not just an application development tool, but an application development methodology. Potential for success will be significantly improved, for example, if one thinks in terms of one's work as a product and not just a project. Picking the right problem is a key success ingredient. The process involves identifying candidate applications, assessing the feasibility of each, selecting the target application, and determining the quantitative justification, as well as how you will know whether you have been successful or not. In all cases, it is important to pre-agree on the goals. Factors in actual problem selection include recognized experts exist and are available. There are one or more user champions for the application. The routine teaching of the task is ongoing with respect to teaching to others. The solution can be validated and impacts assessed. And the problem is bounded. It also needs to be both technically and geopolitically feasible. And there must be a high payoff for success. The problem also must be of the appropriate scale. Typically, the task involved should currently, without a knowledge system, take between 15 minutes and 8 hours. Particularly with your first problem, the results should be highly visible, acknowledged as important, and have a low technical risk. Adequate problem definition is critical. The appropriate scope must be defined. If you can describe the problem using just one sentence, you likely really do have just one problem. It is also important to utilize a model-based approach, recognizing that a single system can service both multiple users and multiple uses, thus amortizing one's investment. The process of application development includes 3 phases. First, developing the demonstration prototype. Second, further developing that prototype and refining it, resulting in a full prototype. and third, productizing the application and delivering the production system. A demonstration prototype shows the breadth of the problem in question, but only goes into depth in one to a few narrow areas to demonstrate proof of concept. A full prototype, on the other hand, incorporates both comprehensive breadth and depth, but has not been completely productized and packaged for delivery. Prototyping itself can be effectively used to get into and understand the problem. Since components of the prototyping will be exploratory, it is important to understand that too much of what you prototype will be thrown away. Even some functions that work well will be replaced by more efficient implementations. A critical consideration is that it is mandatory to keep at least one demonstration prototype at hand. Important visitors may drop in at any time, and credibility is lost by having to fumble around at the last minute trying to put something together. Be prepared. The development of a knowledge system is not actually so different from developing other information systems. In closing, two additional key points are, first, it is continually important to manage the expectations of colleagues and management. And second, one must initially obtain and constantly keep fresh a strong administrative mandate for the development. The process of developing an application is exciting indeed, and I wish you well.
So after the problem definition felt right, you started building the object hierarchies of your knowledge base.
Yes, but we didn't try to complete the hierarchy right away. You can build a lot of unit structure very quickly in KEE. But you may find you get carried away and build a knowledge base with 500 units in 6 hours, only to find that it is difficult to expand and difficult to reason over. My advice would be to start by building a small unit hierarchy, having the rules in the back of your mind. And you should get used to restructuring things as you go. Initial stages of knowledge-based development are actually characterized by two major activities: rapid prototyping and cyclic development. By rapid prototyping, we mean that you quickly build a small working system, test and critique it, and restructure it where necessary. Cyclic development means that individual parts of your system develop in stages. Something may first be a slot, then a unit, then again a slot. You may also find that the different parts of your system, representation, reasoning, and so on, influence each other.
Rapid prototyping. For me, it seems hard to get started. I believe that after having gone through the training materials, I understand the concept of units and slots pretty well. But I still wouldn't know the right way of representing parts of my problem domain. What guidelines can you suggest to help me make these decisions?
Well, actually, there's not necessarily one right way to represent a problem domain. Instead, an appropriate representation is one that makes it easy to perform the tasks necessary to solve your problem. We certainly went through some cyclic development and changes here with the Gates demo. Let's look, for example, at how we dealt with the capacity of an airplane and of how we think this will probably develop as we move from pilot demo to prototype. To help determine possible gates for an airplane, we need to know about the capacity of that plane. We started by storing that information in a slot that is specified for each individual airplane. But we'll probably end up using this design where information about capacity, etc., is then stored at the subclass level. For instance, all planes belonging to this class will inherit a capacity of 85.
So what's the point?
That it's normal to try several representations before settling on one that meets the need in the simplest way.
Well, I think I get the idea, but in working on the representation, do I also need facets like value class and cardinality? Somehow it seems they only get you error messages.
We like to think of facets as giving partial information about slots. For example, when I give the status slot on gates the value class of 1 of, out of service, or OK, I'm saying I don't know what the value is for each gate, but I do know it should be either out of service or OK.
Which can be especially useful if there are several developers.
Right, and this partial information is also used by the system itself. For example, the value class on a slot is used to determine the image choice when you attach an active image, and the rule system will also take advantage of facets and not try to derive values that could not be in a slot because of restrictions you posed earlier.
So the point is that facets give information about a slot that can be used by developers as well as the system itself. I should enter them when they are motivated, since they can be a useful or even crucial part of the representation of my problem domain.
Yes, and don't forget that while you're building, there's often cyclic development in the way you represent your problem domain. Something may first be a slot, then a unit, then again a slot, with a unit pointer as the slot value. But the design of the knowledge base also goes through cyclic development, with different parts of the project influencing each other. Let's have John Kuntz join us.
There are 5 major issues which developers must address in building knowledge systems. First, what's the problem? Second, what's the representation or the description of the problem domain? Next, what are the procedures that we have to use to analyze or to reason about the problem? Fourth is what's the explanation? How do we communicate the nature of our model to our users? And finally, how do we test and validate the model? Let's look at each of these in detail. First of all, with respect to the problem, in one sentence, state exactly what the purpose is in building the application. For example, this application diagnoses failures in mechanical pumps, or the reason for the failure of some pump is some cause. Now, there may be several related problems, such as diagnosing, identifying repairs, assessing the implications of replacing parts in a mechanical pump. State each of these precisely and succinctly. The next, let's look at the representation. What's the actual structure of the concepts and the things in the domain? What attributes describe their measurable and their interesting properties? What behaviors do the objects have? What are the relationships among the objects, such as the class, subclass, the part whole, the supported by relationships? What we're talking about is the units and the slots in the representation. Next, we have to reason over the knowledge. How are the problems analyzed? What are the procedures, the algorithms, the heuristics that we can use to ask the questions? That is, what are the rules and what are the methods that we need to analyze our problems? Next is explanation. What's the form and the style of the interface between the program and the users? What are the diagrams, the graphs, the tables, the reports that will help the user to understand the content of the model and the results of analyses? We want to build these images, these graphs, these tables, which will show us the content of the model and the way that it's analyzed and the results of our analyses. Next is testing. How will the developers verify and validate the accuracy of the model and that the reasoning is effective? Does the model meet the specifications set for it in the problem statement? Is it robust in the hands of users? How do we recommend that developers address these issues? Well, our methodology is to ask the question, what's the most important issue now? And then to go and ask this question repeatedly, and to move our development focus onto the issue which is most important, to focus on the issue which seems to most need attention. Keep in mind that the finished application must give equal development maturity to each of these issues. So if you're making good progress in the development of one issue, it's probably time to go and to look at a different one. Keep moving to the issue which appears most unclear, which is unfinished or unsettling. For each issue, find the solution to the lack of the clarity, to the concern that you have, or simply complete to the next phase, and then ask the question again. At IntelliCorp, we often talk about our anxieties concerning these 5 issues in developing knowledge systems, and we try to focus attention on the anxiety, or on the issue, which has the maximum anxiety. Now, why should you cycle through these issues? Well, in general, each of the issues supports and depends upon the others. For example, the representation is effective to the extent that it supports the problem being addressed, the reasoning procedures, and is understandable to users. In general, the effectiveness of dealing with any of these issues must be addressed with respect to its support of the other issues. That is, it's necessary to ask, what's the important issue now, again and again? Now, when do you ask that question? Well, ask it early and ask it often, every minute or so at first, since all the issues are not very well developed. As the development process advances, ask the question every few minutes and then every few hours. Throughout the development of an application, continuously ask the question, and even after a few months, you should never go more than a day or so without asking the question about what the important issues are. Don't be trapped by the seductive parts of the KEE system and by the problem itself. It's easy and it's fun to create units, key pictures, but it's dangerous to avoid specifying what the problem is and to test the process just because it's hard to do so. In all, keep a balance between the issues and keep asking if what's been done and the direction you're going is the right one. So in conclusion, remember that there are 5 issues. What's the problem? What's the representation? What's the reasoning? What's the explanation? And what's the testing? And then again and again, come back and ask, what's the question now?
Thank you, John. But now I have a question for you, Linda. I saw that you used 2 sets of rules in the Gates demo. Now, why did you decide to use rules at all?
Well, we had several reasons for using rules. For one, we really liked the fact that you can write them so quickly, and debugging is made easy by the extensive graphics. More importantly, we found that the experts we worked with found rules a rather natural way of expressing their thought processes, while they were a bit intimidated by Lisp. But there are a number of things to consider when you make that decision. Before we started, we asked Griff Coleman, Manager of Support, to discuss reasons for using rules as opposed to methods.
When should you use rules and when object-oriented programming in an application? Each of these techniques has its place, and most successful applications we see use both. Your starting point should be to think about the character of the knowledge you are trying to represent, then choose the approach that allows you to naturally put that knowledge into your program. Here are some things to think about in making the choice of rules or object-oriented programming. First, what are rules good for? Rules are easier to write than Lisp code, and they are easier for a non-programming user to understand. This makes them easy to maintain, too. Rules offer a formal way of expressing reasoning, the if-then construct. This form of expression is analogous to the way we see knowledge and thought in everyday contexts. It also allows the developer to express the logic of causal relations. Rule tracing and explanation facilities make executed lines of reasoning easy to follow. Well-written general rules allowing variable values can economically represent a lot of knowledge. They can also be used for several purposes, like explanation, prediction, or answering a question. Rules do well representing knowledge characterized by many independent states and a lack of overall structure. What is object-oriented programming good for? The rich notion of objects in object-oriented programming provides a useful approach. For this approach to work, there must be clearly definable elements in the domain knowledge, and these elements must have specifiable behavior. If interactions between the objects are complex or not completely defined, then object-oriented programming is surprisingly effective in modeling the possibilities. Unlike rules, which directly describe causal relations, object-oriented programming implies interactions in the characterization of the objects. An application developer can easily modify and extend the behavior of an object if it inherits pieces of Lisp code down from more generally specified objects above it in the class-subclass hierarchy. Object-oriented programming is a better choice than rules for representing procedures or doing computations. Coding directly in Lisp frequently results in a faster application. You also have access to Lisp debugging facilities. There are some aspects of applications, like building an interface, where you obviously want to work directly in Lisp and not pay the overhead of rules. Use object-oriented programming when you want to represent behavior, procedures, or computation. It is appropriate for expressing knowledge that can be broken down in some detail. Its advantage is representational richness, efficiency in extending or modifying the code, lack of overhead, and greater flexibility. In summary, rules and object-oriented programming each have their strengths. You should expect to use both techniques in building your application. The most important questions are, what is the character of the knowledge I'm trying to represent? And where do each of these techniques have strengths which appropriately match up with this representational task.
Well, I'll come back to this rules versus Lisp methods question. Maybe you could first tell me a bit more about when you used forward chaining and when you used backward chaining in gates.
Well, in general, you use backward chaining when it's natural to begin by asking some questions. We felt that was the case for identifying possible gates. It's natural to start by asking something like, what are the possible gates for jet 1? On the other hand, you generally use forward chaining when it's natural to start by stating some new facts and finding their consequences. That seemed to be the case for keeping track of the relationship between a gate's resources and its status. It's natural to report that the status of Agent 1 is unavailable, and then let the system find the consequences, if any.
Well, that's a start. I think I get the basic idea about using rules.
And you'll keep learning more as you go on. I once heard someone say that KEE has a low floor but a high ceiling. That means that you can do something with the system on the second day. But in contrast to less powerful systems, KEE's rule system is very flexible. You can fine-tune your rules to suit your needs and to solve the problem in the most efficient way. Take the interleaving of chaining. Sophisticated problem solving often calls for both sorts of reasoning. For instance, you may expand this system and add a knowledge base that diagnoses the most common problems with a jetway. You could use one set of rules to diagnose the problem. You could then go on to recommend a repair procedure using a different rule class. Since you end up calling only the rule class you need, depending on the preliminary diagnosis, interleaving chaining and working with different rule classes can greatly increase the efficiency of your system.
Which has been one of my concerns all along.
Which is why I also want to point out agenda controllers and the rule compiler.
Agenda controllers?
Yes. Agenda controllers determine what search strategy the system will use. For example, if you know that certain rules are most likely to find the solution to a problem, you may want to weight them to let the system know it should use them first. Or, when you backward chain to prove a goal and are only interested in one answer, a depth-first search is usually, though not always, most efficient. Let's assume I backward chain and ask the system, is X true? Well, the system finds two rules that could be used to prove this goal. It goes to the first rule and finds that it in turn has premises that need to be proved true. Now, there's a choice. If you're in depth-first mode, which is the default, the system will go this path until it is successful or cannot go any further. Otherwise, it will try the second branch next and basically jump back and forth here.
I can see how this could be useful.
Yes. As for the rule compiler, that's something you use when your prototype or your application are rock solid, and it again will greatly speed up your system. And to find out more about any of these topics, you can go to Rule System 3 Reference Manual. But let's ask Randa Mulford, Manager of Training Services.
Once you've decided to use rule-based reasoning in your application, you should keep a few things in mind in order to use rules effectively and appropriately. First of all, let the rule system do what it does best, which is uncover information or answer questions in a relatively unordered way. The rule system is designed to search for information, especially in cases where you don't know ahead of time just what information you're going to need or exactly where you're going to find it. Don't try to use rules to implement procedures or control structures where the sequence of action-taking steps is important and where there's little need to search in an open-ended way for information. You should use methods to implement procedures like that instead. Secondly, more rules are not necessarily better. Generally speaking, having lots of very specific rules with no variables in them is less effective than more general rules which include variables. Again, the point is to let the rule system do the work of figuring out the specifics for you by finding the appropriate bindings for variables in your rules. You can help the rule system do its searching more efficiently by including one or more premises in your rules that limit the possible bindings that the rule system will try for the variables. For instance, if you have a rule something like this, $X could be bound to the name of any unit which has an engine condition own slot. If, however, you add a new first premise to the rule stating that X should be a member of the class automobiles, then the rule system won't spend any time reasoning about other kinds of objects with engines when this isn't appropriate. Another important issue is the relationship between your rules and your frame-based representation. In developing an application, you'll find that the way you represent objects in your system as units or slots or whatever will not only influence how you write your rules in terms of what the premises look like, but also that the representation can affect the efficiency of reasoning. To take a simple example, consider how you might use maximum cardinality specification to help a rule run more efficiently. If you've specified a maximum cardinality of 1 on a slot, and the slot has 1 value, then the rule system won't waste time trying to come up with other values for the slot. The representation tells it that it already has as much information as it should need. If the cardinality specification weren't there, then the rule system would go on to look for all possible slot values, even though you're really only interested in coming up with a single value. In a similar way, using a value class specification on a slot helps the rule system limit the bindings that it tries when it looks for possible slot values, and this will allow the rule system to work more efficiently. The moral is to consider ways to refine your representation of units and slots so that the representation supports focused and effective reasoning. There are other techniques for fine-tuning rule system performance that you'll want to have in mind when you're developing your application. Sometimes it's beneficial to constrain the rule system search by making some rule premises or conclusions unavailable for chaining. In extreme cases, blocking chaining on a particular part of a rule might be the only way to avert an infinite loop in your reasoning. Fortunately, there are a number of ways of blocking chaining in rules in KEE. Try to organize your rules into several rule classes arranged in a hierarchy. This will give you the flexibility to focus your reasoning at different levels of generality, using a small set of rules for a well-delimited problem and a larger set for less specific reasoning. You can use agenda controllers to control the overall search strategy while your rules are running. For example, agenda controllers let you choose between a depth-first search or a breadth-first search, depending on what's appropriate for your application. Try out a variety of search strategies and control structures to fine-tune the rule-based reasoning of your application.
Thank you, Randa. You know, I'm starting to feel a lot more comfortable about using rules, but what about Lisp? I mean, I'm not a programmer.
Well, looking at this demo, you may think I hacked Lisp for the last 2 years, but actually, a lot of the code in this demo uses key user functions, like put value and get value, that directly manipulate objects like units and slots. You'll probably want to learn some Lisp as you move along, but I sort of eased into it. To get started, you should know your machine and your editor, and if possible, be able to read Lisp functions others have written. And you're on your way.
Sounds good. But how about object-oriented programming? Now, what's that?
Well, actually, that's the best part of working with Lisp and KEE. You can take advantage of the unit hierarchies you establish to ease your programming. In object-oriented programming, the code lives in the objects as a slot value and is inherited just like other slot values. You then send a message to an object to execute a certain behavior, and the code will be picked up. And the best part is that because of this modularity of code, you can reuse it easily or modify it slightly for special cases where appropriate. For example, we have the createJet method here in the jets unit, which prompts the user for the name, type, and capacity of a new jet. I can reuse that and make a createGate method that would live in gates and take as input the name and capacity of the gate as well as the agent and jetway assigned to it. I keep the first part of the code and add some code here.
I see. So that means I can reuse code by copying and modifying a method, like you did to create gates.
Yes, and you can also refine code at certain levels in the hierarchy. For example, you could have private planes and commercial aircraft as subclasses of jets, and they would have slightly different behaviors.
Well, I'm ready to start building an application. Anything else I should know?
Well, I've asked Tom Benura to come in and talk to us about some aspects of object-oriented programming that beginners are typically interested in.
We in applications rely heavily on object-oriented programming. As we've already discussed, it encourages reuse of code and specialization of behavior. It also makes it easy for others to see what's going on. And besides, for some problems, it's very natural to think about objects as having behavior. Simulation is an excellent example. I'd like to give some very concrete advice about object-oriented programming style. First, keep in mind that you're not writing a large program when you write a method. A method should be a small piece of code which allows the object to do something very specific. If your methods are very long or have lots of conditional code, you may need to consider additional subclassing, writing another method or simplifying the method. Consider where the method is to reside. It sounds simple, but it's easy to forget. The method should reside where the action is to happen. Also, be aware that some methods are appropriate only on a class. For instance, a create member of class handler. This should be an own slot in a class and not inherited to its members. Finally, get into the habit of using function names as the value of a method slot, not lambda bodies. This will make your life easier in many ways and is worth the additional trouble of file maintenance. And finally, over-comment your code. Indicate the method handler and what you're trying to accomplish. You also might indicate what objects may be sending this message. If you keep these things in mind, I think you'll find that object-oriented programming is an intuitive, fast, and comfortable way to work.
Thank you, Tom. Now, one thing I was really impressed with is the interface you built for this demo.
Ah, that really took some thinking. We went through 3 designs and we learned a lot in the process, and now we're pretty happy with it.
So, what did you learn?
Well, let's just look at some of this together. Here's the first interface we had. 2 screen-sized panels, the gate assignment panel here and the panel for Concourse 1.
I can see the first problem immediately. You don't want information that should be visible at the same time shown in overlapping panels.
Right. And on the panels, there are just boxes with instructions or facts. A lot of reading going on here. There seemed to be no underlying design principle. If you mouse on something, different things can happen. You may get a choice menu, or the system just performs an action. And the arrangement of information on the screen isn't very good either.
Could you summarize these points?
Yes. I think you should have all relevant information on one screen, have a better arrangement of information, use underlying design principles consistently, and use more pictures, fewer words.
So you built a second interface.
Here it is. Almost no overlapping of relevant information. And watch how I interact with this. I can choose an aircraft for assignment, and it will highlight and actually move back and forth, depending on whether the gate in question is out of service or not.
I like that. Now, but why didn't you keep this interface?
It looks like a toy. See, over here on the left is room for 4 airplanes. Where would the next one go? How about the next gate? The key problem is extensibility, which we actually had in the first interface. This one also needs a little more information, and perhaps fewer pictures. But that sort of depends on your audience.
Extensibility. Hadn't thought of that. So you went on to the third interface, which we've been watching all along.
Right. Here it is. Extensibility is added in 2 ways. We provide for multiple terminals, since a terminal panel is brought up depending on the airline in question. And you can choose planes and gates via menus, which give room for expansion when extra jets or gates are added. The assignment panel only shows information for the airplane that is being assigned. Again, this makes the interface extensible, and you can show more information. The control panel is more consistent. Since we have menu choice actuators here on the left, the 2 images in the middle can be used for explanation, and the 3 on the right for actions affecting the whole knowledge base. We've gotten some pretty good feedback on this one, but since it did take quite a while to get there, we asked Marilyn Stelzner for advice about interface design.
Since the gate system is a demo, the interface you saw there is fairly simple, and the trade-offs the designers made between the different interfaces were fairly obvious. Designing usable interfaces for knowledge systems applications is critical to the success of a project, and you should be sure to allow sufficient time in your schedule to try different interface approaches as you just saw, and to fine-tune the style of interface you settle on. In many of the interactive knowledge-based systems we see developed with KEE, fully 50% of the application, and presumably the time required for its development, is involved in user interfaces. One thing you can expect to see in a fielded application is more than one interface. These interfaces may be designed for performing different tasks that are interrelated and that share the same knowledge. You could also have different interfaces for different classes of users. For example, many applications in the manufacturing area are used by both planners and shift supervisors, but those classes of users will probably have need for slightly different information. No matter how many different tasks your application supports, it's important when designing a user interface to keep in mind the end user's overall objective. In the gates demo, users assign aircraft to gates, but their goal is to minimize delays. The interface needs to give them the data to assess how well they're doing. In other applications, users may perform a series of subtasks that all contribute to the accomplishment of some higher level task. It's frequently possible to skip some of the subtasks or to perform them in slightly different orders. When you are designing the user interface for this kind of application, it's important to provide the user with a roadmap indicating what the possible next tasks are and how each subtask relates to the accomplishment of the overall objective. At the same time, your users will get frustrated if you try to lock them into very specific paths through the subtasks, and if you don't let them digress when they want to. In terms of general guidelines for user interface design, be sure you talk to potential users of your application as well as to experts early in the process. Experts won't have problems with things that might be difficult for less experienced users, and experts will have a hard time judging what beginners need to know. I could go on and on with things to keep in mind when you design your user interface, but there's one hint that many people don't follow initially and wish they had later. It's tempting to mix domain knowledge with a knowledge-based interface, especially when you're using key pictures. For example, you might have a key picture unit that represents an airplane, and you might put airplane slots on that same unit to avoid creating an additional unit. You'll probably run into problems with this approach later when you extend your application, when you add additional interfaces referring to the same airplane, or when you try to make significant changes in the interface style. Some applications will be deployed as embedded systems, where the entire interface has been removed, and you'll find it much easier to do that if you have separated the domain model from the interface to that model. This approach may seem like more work initially, but you'll save time and you'll have a more extensible application if you follow it.
As you now start to build your system, don't forget that there is more in the KEE system than we could cover during this training. As you work, you may want to learn about using worlds for planning problems, using key pictures for interface design and animation, and working with other packages such as Key Connection or SimKit. And even as you start, don't forget to think about portability. You'll probably want your knowledge base on more than one machine in the end. Here's Joe Robinson to comment on portability issues.
I often get questions about porting and compatibility between machines. Here are some guidelines. First, remember to develop your application using only key functions and subsystems. Customization should be done at the key user function level. Windowing should be done in common windows and not in the machine's native environment. Stay with strict common list functions. Don't use inner list, flavors, or Zeta list windowing system functions on the list machines. Don't use Lisp vendors' extensions to common Lisp on the workstations. Make sure that your function files have the package set appropriately. That way your Lisp functions get evaluated into the key package. We always recommend that you use relative window sizing. This means that instead of placing a window in the middle of the screen by specifying the exact pixel coordinates, you would say 1/2 times window stream height of key root window. By doing this, you ensure that your interface will be proportional to the size of the display. This is important since even the same types of machines have different monitors and vastly different resolutions. When you design your interface, make sure it would fit on a smaller screen. You may want to layer your interface so that you don't have the very many windows on the screen at the same time. You might design the interface so that there's a series of shrinkable windows. When you actually move to a smaller screen, place all pictures in the lower left corner of the screen. This will allow them to be visible on the smaller EGA type of monitor. Finally, single process lists cannot support mouse move methods. This means that hotspots are not boxed when you move the mouse over them. Common windows may not be completely implemented in some lists. For example, inner and clipping regions for common windows are not implemented on some platforms. Check your release notes for details. List machines generally allow a very wide range of fonts, most of which are not portable. Check for these in the key picture and active image units in your KB. Remove custom fonts from text and list function files. For example, some people place their function names in bold and their comments in italics. These fonts will need to be removed. Use the predefined font global variables. Examples of these are the key picture variables star medium font star and star medium bold font star. You may also define your own global variables and then place the definitions in their own file. You can then modify the definitions when you go to a new machine, while still retaining the references to the variables. You can always determine the existing fonts on your current machine by evaluating the function install-fonts. Use the function openFont and KeyFont as documented in the Key Interface Manual to access particular fonts. The key knowledge bases should move easily when porting, but you will always need to at least recompile your function and kbname.list files. When you're porting your files back and forth between two machines, it is sometimes useful to put the machine-specific code into one file. This way, the majority of the code can be the same, and all changes can be made at once and in one file. Porting from inner list to common list is generally more difficult than from one common list to another common list. IntelliCorp does have some utilities to aid in this latter process. Make sure that you are aware of any file name limitations on both the current and the target machines. Some machines do not support dots or dashes in their names. Some allow only 3-character extensions and have limits as to the length of a file name. You will need to convert all of your path names to the proper syntax for the target machine. This is especially important for wrappers that you have for loading your KBs. It may be useful to define variables in a file that are the physical path names. You can then reference these variables in your wrapper code. When it is time to make changes, they all can be done in one place. These Xerox list machines use a reference counting garbage collection scheme in which circular structures cannot be collected. This may cause some infrequent problems since Key does use circular structures. Many of the lists running on workstations have stop and copy garbage collections. This means that when Lisp has cluttered itself up, it will stop what it is doing and clean up. Your application may want to explicitly call the garbage collector at opportune times. These are most of the issues in porting Key applications. If you follow these guidelines, you should be well on your way to developing portable and compatible code.
Thank you, Joe, and good luck to you all as you develop your applications with Key.